I'm going to start my story with classical Galois theory. So this is something I had learned in undergrad. Classical Galwa theory is about field extensions. So I have my favorite base field K, and I have an extension of it which satisfies some technical conditions. It has to be, I've put finite for the time being. We'll be more flexible about that later. But the important thing is that it's separable and normal. And if you've never seen Galwa theory before, I can explain what those properties mean specifically, but just think of them as technical conditions for now otherwise. And when I write k less than or equal to L, I mean L is a field which contains k as a subfield. So the fundamental theorem of Galwa theory says there is an order reversing correspondence between the intermediate subfields of L over K. So that's fields which live as subfields of L and contain the specific subfield K, and a certain lattice of subgroups where this gal L over K is the Galwa group, which is to say the group of field automorphisms of L which fix this subfield K. And how this correspondence works is it sends any subfield big K of L to the corresponding Galwa group, because this lives inside the Galwa group of the larger extension. And in the other direction, it sends any subgroup of the Galwa group to the subfield of L, which is fixed by all elements of that subgroup. So, for example, if I take the maximal subgroup, so that is the whole thing, then the only thing that is fixed by all elements of that is little k. So that's thanks to these technical conditions. So let's have a look at this in a special case. The rationals extended by adding the square root of 2 and the square root of 3. And so the special case of this theorem says that there is an order reversing correspondence between the lattice of intermediate subfields in here and the lattice of subgroups of this Galwa group. And Galwa theory obviously has more substance to that, so we need ways to calculate what this group actually is. Useful because once this group is calculated, it tends to be a lot easier to work with than the full fields, which can be q root 2 root 3 has rather a lot of elements, whereas it turns out this is just the Klein 4 group, which is a lot more manageable. So here are those lattices. Now, the idea that Galwa theory is about these lattices, so all we care about are the inclusions, is a direction that this has been generalized. So you might have heard of Galwa correspondences or Galwa adjunctions, which are between partially ordered sets. So a Galwa correspondence refers to an order of reversing correspondence between ordered sets. But what I want to convince you of, if you haven't seen this already, is that there is some extra categorical structure here, which it helps to keep track of when we want to generalize this in other directions. So let's have a look. So as I mentioned, we had those technical conditions of separability and normality. And these are exactly the conditions for the Galwa group to be able to see all of the extensions. What do I mean by that? So an example of an extension that fails to be normal, I think, is if I adjoin the cube root of 2 to the rationals. Because, so let me stop sharing. So if I look at, someone should correct me if I'm getting normal and separable mixed up. So if I look at this field extension, I can't apply the fundamental theorem of Galwa theory to this, because when I apply an automorphism of, when I try to find automorphisms of Q extended the cube root of 2, which fix Q, then, well, firstly, I know that the cube root of 2 satisfies x cubed minus 2 equals 0, or x cubed equals 2. And because any field automorphism preserves the field operations, that means that whatever the cube root of 2 is sent to, it still has to satisfy this equation. But because I've only added the cube root of 2 and not the complex roots, there is only one element. This cube root of 2 is the only solution to this polynomial in this larger field, which means that that's the only place it can be sent to. And because any automorphism of this field is determined by where the rationals are sent, and we know that they're fixed, and where the cube root of 2 is sent, that means that there are no non-trivial automorphisms. And so the Galwa group, well, can't see that this extension exists. Let's go back to the slides. You've seen Galwa theory before. This is all very basic. So let me get to what I actually want to say. So in this correspondence, the group on the right-hand side can't see the fields are involved, which fields are involved. So I could replace the rationals with any of many other base fields. So I need, for example, the properties of the polynomials whose roots I'm adding to not be broken by the field I'm moving to. So, for example, I don't want to be in characteristic 2 or 3 because that would that would break the example. But I could replace it with the field with 25 elements, for example, and the picture would still be the same. And that suggests that actually everything that's happening is purely at the level of the categorical structure, or at the very least, what we've seen so far, at the level of the ordered structure. There's also the fact that this automorphism group is really acting on a discrete set. More on that in a minute. And if we look at these actions, then we can identify what categorical structure is the right one to be looking at. So here is the lattice from before. And if we look at the elements of the Galwa group and what they're doing, we see that F, we could take F to be the automorphism which switches root 2 and minus root 2 here, recalling, as I argued in the cube root of 2 case, that the square root of 2 has to get mapped to something which is also a square root of 2. And I can set G to be the one that permutes the square root of 3 and minus the square root of 3. And then we kind of see that this entirely determines the action of F. So I can redraw this lattice. Q root 2, root 3. Q root 2, Q root 6, Q root 3, Q. Okay, and I can instead identify this with the action of the Galwa group. If I take the pairs, let's just go with plus or minus square root of 2, plus or minus square root of 3. If I just look at this 4-element subset, then the action of the group is entirely encoded by what's happening on these pairs. And when I look at these subfields, there is a mapping of the action. So I can write the correspondence as here. I just take the first projection, plus or minus square root of 2. Here I take the product of the 2 entries of these pairs. So I get plus or minus square root of 6. And here I take the second projection and get plus or minus square root of 3. And then at the bottom, I can just take, let's say, 1. Okay, so why have I drawn this picture? What's my point here? There aren't canonical choices here, but I can choose a discrete subset of this field which determines the action. And actually, the picture I've ended up with on this side, if I look at the action restricted to these elements, is the lattice of, or if I add some arrows, the category of transitive actions of the Galwa group for this field extension. So this is the Galwa group here is isomorphic to the Klein 4 group. And so I have my 4-element set, which is isomorphic to the action of the group on itself. Then I have the cosets of let's say the left cosets of the 3 subgroups, and then I have the trivial action. And this represents all of the transitive actions of this Galwa group. And so in particular, there are some G-set automorphisms here, which I can add to this picture. And what I find is that I can also add these on this side. I'm not going to do it because it's already messy enough. But this is really saying that there's an equivalence of categories between the extensions, the category of field extensions and the category of transitive actions. And that's the kind of identity that I am going to extend. One. Okay. Can you still see my screen? Hopefully. Yes. Okay. So this is my claim. This is how this all shakes out. And so this is a restatement of, this should still be classical Galwa theory. This is a restatement of the correspondence, but where now I'm keeping track of some extra morphisms. And you'll notice here, rather than going to the subgroups, I'm going to the quotient. So that is the set of cosets of the Galwa group with respect to the subgroups. So it's a subtly different thing on the right-hand side. So now let's move forward in time a little bit and go to Grothendieck's Galwa theory. So Grothendieck based his extension of Galwa theory on the observations I made so far. But rather than just looking at the transitive actions, he looks at the actions on arbitrary finite sets. So rather than just including the extensions which are fields, we have finite K algebras. And this is in order to extend this situation to, for example, the algebraic closure of your favorite field. So if I start on the group side instead here, I take a profinite or finite group, and I look at how it acts on finite sets. Then I get a category C, which has some nice properties. So it's finitely complete and co-complete, just because I can take products and co-products of group actions and equalizers and co-equalizers are well behaved. There's a strict epi-mono factorization system. So if you haven't encountered factorization systems in categories before, what that means is that any arrow in my category can be factored as a strict epimorphism, so a surjection, followed by an injective homomorphism. And this is kind of inherited from the fact that we're acting on sets. And so I can just take the image factorization. And kind of the crucial thing is that this category C has at least one functor to set, which is conservative, so reflects isomorphism, and it preserves this limit and co-limit structure. So this functor is the underlying set functor, which in the example I gave earlier, we had the Klein 4 group, we had its transitive actions, and we can just take the mapping which forgets what the action is. So using this characterization, he was able to capture also a parallel of Galois theory for covering spaces. And this extends the notion of fundamental group. So you can think of the fundamental group of a nice locally path-connected space as coming from Galwa theory for the category of covering spaces of that space. So I'll draw a picture to illustrate how that works in a minute. But also you can use that to extend Galwa theory to algebraic closures. And it turns out Topos theory is a good setting to generalize that so that you can define the fundamental group of a Grothendieck topos. Let's have a look. So, yeah. Equipment's falling apart. So, what am I talking about? Let's say I have, let's look at the circle because it's nice and easy to draw. So, thinking of this as a nice path-connected space, there are plenty of covers. So I have my universal cover, the real line. I've got some n-fold cover by a circle. And the point here is that if I take any point on the circle, I have to choose a point, and I look at the fiber over that point, then I get a discrete set, a finite discrete set, except in the limit. So let's just take the finite covers in this case. I get a finite discrete set on which the fundamental group acts. But similarly, that's true if I take the double cover by two circles. So I have a fiber. It just so happens that the fundamental group acts trivially on this fiber. So the idea of Grothendieck's Galwa theory is to say, take my space, look at the finite covers of it, which are nice enough, so the finite Ital covers. They form a category which has a suitable functor to set by looking at the fiber over a particular point. And I can use that to derive a fundamental group. And this gives a derivation of the fundamental group which doesn't look at paths in any way, which is independent of paths. And that makes it easier to generalize to other situations where I have rather than a base space, I have a base topos. So if you're vaguely aware of topos theory, you can think of toposes as generalized spaces, and there are some ways in which that's more true than others. And so having this alternative way of expressing the fundamental group gives you something that you can actually calculate for toposes. So back to the slides. So we can extend these ideas a bit further. In particular, beyond profinite groups, because we can look at actions of groups which aren't necessarily profinite, and they still give nice categories. And there are still situations where we can get a correspondence between categories of actions of a topological group and some other category of interest. So here, rather than looking at all of the finite things, we return the transitive ones, which when our group is significantly larger, like if we're taking the reals with addition, say, is something, there are too many extensions. There are too many ways for that to act for it to be captured by the finite actions. So we return to looking at the transitive ones, which ultimately generate all of the others anyway. So Caramello's framework and my framework, which we'll get around to, live in the setting of Topos theory. I put the slide in light orange because I don't really want to talk too much about Topos theory, partly because it scares people away. So if you know what a pre-sheaf category is, fantastic. You can think of a topos as a left exact reflection. The important thing that you'll need to know is that even without knowing what a topos is, I can build a topos from some data, which is called a site, which consists of a category C. The highlighting is really not great on these slides. Category C and some extra data called a Grothendieck topology. I'll come back to that later. But the point is, whenever I have any old topos, any old Grothendieck topos, I have at least one way to present it in terms of a site consisting of a category and a Grothendieck topology. So, why a topos is relevant to the situation? If I have a group, I can look at its actions. This should come as no great surprise. I've been talking about them for a while. And hopefully you know what an action is, otherwise you might have been confused so far. But another way of presenting the data of an action is to think of G as a category with a single object. So the elements of my group are now, I'm now thinking of as arrows from that unique object to itself. And the multiplication of the group is the composition of those. And an action is then a functor from that one object category to the category of sets. So that one object gets sent to some set. Each arrow, so each element of the group, becomes an automorphism of that set. And so if I look at the category of all these actions, it is of this form. So this means the category whose objects are functors from G to set. There's an op here because I'm thinking of right actions. And the morphisms are natural transformations, but in this case, they correspond to homomorphisms of actions of the group. So even if you don't know what a topos is, hopefully a category of actions shouldn't be too scary. So if I have a topology on my group, and I do mean it this way round, I'm thinking of a group being equipped with a topology rather than a group in the category of spaces. Then I can look at the actions which are continuous with respect to that topology. So that's just a particular condition on any given action. Homomorphisms automatically respect continuity. There's nothing extra to check. So I get a full subcategory. So I have some category of continuous actions, and I have my category of all actions, and I have this forgetful functor that just forgets that I was looking at continuous actions. And this functor has a lot of nice properties. So it preserves finite limits. It's closed under subobjects because any subaction of a continuous action is continuous. And it also has a right adjoint. So if I take any action of my group, I can just look at the elements in that action at which the action is continuous. Or in other words, I can send my G set X to a set of elements such that the subgroup which fixes X is open in my topology. And it turns out that these conditions together, so these conditions on V and the existence of this adjoint, are enough to ensure that this is another instance of a topos. And again, without scaring you with too much topos theory, it's not only a topos, but it's also with a bunch of nice properties. So for example, it is still the case that any action, any continuous action, can be decomposed into principal actions, so actions generated by individual elements. And that's what I mean by saying that the topos, this category, is generated by the non-trivial subobjects. And there are a bunch of different ways of expressing these because, of course, any G set with a single generator is going to be transitive. So it's also two-valued, topos that is, which means that the terminal object, the trivial G set, has no non-trivial subobjects. So it turns out this is exactly the one element set with G acting trivially, and the only subsets of that are itself and the empty action. So the reason I mention these properties is that they characterize the situation. So if I have a topos with these properties, and I have a point, which again, a point is a geometric morphism from the topos of sets. Those are scary words. What I mean is there is a functor from my topos, cont g tau, to the category of sets, which is just a forgetful functor. So if I take any action, I can look at its underlying set. And I can characterize the properties of that functor, and that's what I mean by a nice point. So if I have a topos with these properties and a functor with these properties, then I can recover a topological group. And this is exactly analogous to what was happening in Grothendieck's Galwa theory, where given a category with nice enough properties and given a functor to the category of sets, also with nice properties, I can recover a group from that. But you have to choose a point. There may be more than one. But at least in the discrete case, there is exactly one representative up to isomorphism. So if we're worrying about the fundamental group, for example, then it doesn't matter particularly which point we choose. So now I mentioned that any Grothendieck topos can be presented by a site. And it turns out that to generate a topos with the nice properties I mentioned, the canonical choice of site, that is I was having a discussion about the use of the word canonical in maths on a Discord server recently. So I'll go with canonical. A reasonable choice of site for such toposes is to take C, a category having reasonable properties, where here reasonable means having the joint embedding property and the amalgamation property. So again, technical conditions which are necessary and sufficient to make this construction work. In particular, in order to be able to equip C with a particular type of Grothendieck topology called the atomic topology. So, given this, I can construct a topos on this site, and there's a natural functor from my category C into this topos. And the reason I choose a site of this form, without having given you enough details to really know what this is, without if you haven't seen it before, but the reason I choose these properties is because there's a canonical functor which sends each object of C to an atom of this topos, which in the case of group actions, the atoms are the transitive actions that we're interested in. So I'm looking for the kind of correspondence or the kind of functor that sends the objects of a category I'm interested in to the atoms, which, when this turns out to be a topos of actions of a group, will be the transitive ones. And so I can eventually recover the kind of correspondence that I started with. So yeah, that's basically the content here. If I can find a site which presents a topos of G actions, then this functor sends each object of my category of interest to a principal or transitive right G set. Now, having fixed my topological group G, I can index these transitive G sets by the open subgroups of G. Because of the condition for continuity, any transitive continuous action is going to be isomorphic to is going to be isomorphic to the cosets of G with respect to some open subgroup. There's another way of thinking about this, which generalizes better. So I want to do a quick sketch. So I've said that transitive G sets, which are continuous with respect to tau, correspond to open subgroups. But actually, when I quotient G by an open subgroup, what that's really doing is taking the quotient of G by an open right congruence. So what do I mean by this? If I look at G with its canonical action, action by multiplication. Okay, I can think of this. This is the canonical G set. But when I take quotients of this, I can think of any quotient as being, let's call this n, the quotient by some equivalence relation, right? And this equivalence relation still lives in the same category of G sets. That is, this is a relation which is closed under the right action by multiplication. Hence, it's a right congruence. And so whenever I take a quotient by an open subgroup, what I'm really doing is taking the quotient by one of these open right congruences, which looks exactly like the set of x and y, such that x, y in the same coset with respect to h. And the reason we can transfer between these is because all cosets have the same size. So I only need to check the one that contains the identity, and that determines everything. But when we go to monoids quite shortly, then there are some non-trivial right congruences in the sense that they're not determined by the neighborhood of the identity. And so we need to keep track of all of the equivalence classes in order to be able to still see what's going on. So returning to our original situation, I can take C to be the opposite of the category of intermediate subfields or field extension. I need to take the opposite because the quotient maps go in the opposite direction to the inclusions of the subfields. And that has all of the properties that I'm looking for. And so I can, and by a similar argument to the one I gave earlier, I can find the mapping from those two discrete actions or to the underlying set of discrete actions, and hence construct this point to get all of the data I need to recover classical Galwa theory. So how does the fundamental theorem come out of this? The fundamental theorem of Galwa theory is then an exposition of the necessary and sufficient conditions, so the separability and normality of the extension, to make sure that this this site. So C always has the technical properties that is needed. But to make sure that the atomic topology contains enough information, is fine enough to be subcanonical. So remember this functor L that I mentioned earlier. I can always define this for a category C consisting of field extensions. The problem is that unless those technical conditions are satisfied, this functor L can lose information, which is to say I don't get an equivalence of categories, I just get a functor. So the fundamental theorem is saying under these technical conditions, L is an equivalence on its image. So moving on to monoid actions. I'm over halfway through, so it's a good thing I included the short version. All of the Topos theory works for monoids too. So you can think of the actions of a given monoid as being functors from that monoid viewed as a category into the topos of sets. I get the same construction as before. This, incidentally, is a topos, but it's again just the actions of my monoid on sets. And I again get this adjunction when I equip my monoid with a topology between the category of all actions and the one which are continuous with respect to my topology tau, which again satisfies all of the conditions I need to make sure that this is still a Grothendieck topos, which I want because I can do Topos theory with these things. So what's different is that the special properties that I need obviously look a little different. So rather than, I can no longer identify principal actions with transitive ones. Well, that's not exactly true. I can, if I have a principal action and I start from my generator, I can use the action to get to any other element. But the point is, given any arbitrary pair of elements, there may be no way to apply the action of the monoid to get from one to the other. So really, I want to focus on these principal actions, or cyclic actions, if you prefer. The observation about two-valuedness still applies. So once again, if I have a topos with these properties, I should have mentioned supercompactly generated is the categorical way of expressing that something is principal, aka cyclic. So supercompactly generated is saying that there are enough of these to cover every object, which translates to saying that any continuous M set is the union of the M sets generated by each of the individual elements, which is pretty easily checked. So I again have a nice point, which is just the underlying set functor again, and I can recover a topological monoid from a topos with these properties and that data. So now what I want to do is essentially what Grothendieck did for the finite covers. I want to identify the properties of these, of the categories which give these toposes, so that I can eventually obtain the equivalent of a Galwa correspondence, but replacing my topological group with a topological monoid. So here I'm again taking a category C with suitable technical properties. A Atomic Topology J, which is just generated by single arrows. So the data of which arrows generate covers in J I have omitted, but I can go into in more detail if you're interested at the end. And the point being that just as in the group case, each object of my category C gets sent to a cyclic action when this topos is equivalent to the topos of actions of my topological monoid. So this kind of explains the reason why I wanted to talk about right congruences, because when you've shifted to monoids, you have no choice but to talk about open right congruences. So rather than talking about the principal right M sets themselves, it's useful to look at the open congruences instead. And it turns out that there is a natural way to endow the category of such congruences with this categorical structure equivalent to that on the principal right M sets. And essentially how that works, I don't have it on the slide, so I'll write it down. So I have my relations are an S on my monoid M. So that's, there are two product projections. So I have an arrow from R to S being indexed by an element of M such that R is contained in M star of S, where what this means is the set of pairs A, B such that MA, MB is in my relation S. Okay, and this is modulo S, I believe. Okay, and this categorical structure, if I take the quotients, I can identify these with the right M set homomorphisms between the quotients. So M over R, M over S, and I get a morphism in the same direction. Okay. Vague picture, but it's nicer to, the reason I would want to do this is because it's easier to keep track of the collection of congruences on my monoid than to try and work directly with quotients, because there are a lot of different ways of, there are a lot of different objects isomorphic to this, to any given quotient. So I want to keep track of the congruences. Okay. So how much is left? So now all that's left to do is to characterize these. So what do these categories actually look like? They have a particular kind of colimit called funneling colimits. So a funneling colimit is one where I have a bunch of arrows, some of them parallel to each other, going into a single object. And so, well, maybe I'll draw it in a minute once I put all the conditions up. I have a factorization system on my category again, and it happens to look a lot like the one for Grothendieck's Galwa theory, which is a strict epi mono factorization system. So it turns out that these strict epimorphisms, I haven't told you what they are, but they're exactly the ones that you can express in terms of funneling colimits. So again, I'll demonstrate that in a minute. And finally, I need this condition that for any pair of objects, there is a third object which jointly covers them. So what do these look like? Funneling colimits. So that's saying that whenever I have a diagram that looks like this, so I have a single weakly terminal object and then a bunch of arrows going into that. The colimit of a diagram of this shape, let's call it a funnel, I can encode just as with coequalizers, which are a special case of these. The data is entirely determined by a quotient map coming out of X0. And this is a strict epimorphism. So this is, you can give this as a definition of a strict epimorphism. Or there's another definition which says a morphism is strict if it's the joint colimit of all of the pairs of morphisms which it co-equalizes. So instead of looking at funnels like this, I could just take a bunch of parallel pairs and say that this is a morphism which joint co-equalizes them all. So the factorization system is saying that if I have x to y, I can factorize this as a strict epimorphism, followed by a monomorphism. And the final condition is saying if I have objects x and y, there is some object, let's call it xy because I'm not going to need the notation particularly. It's not unique, but there is some object which has strict epimorphisms to both x and y. And these conditions characterize the transitive actions of a monoid. So I think I have one more slide. So they're all necessary conditions, therefore. But it turns out they're also sufficient as long as C is small enough. So the point being that in order to construct the nice point that I mentioned, something to act as the underlying set functor from which to recover the monoid, I need to construct a filtered diagram in my category C. Or rather in the opposite of this category. And so when C is small enough, so say when C is countable, then I can actually construct such a filtered diagram which has all the properties that are needed to produce this point and therefore extract a topological monoid. Fantastic. And so ultimately the consequences of that are I now have some technical conditions, but they're not too complicated as technical conditions go. And if I can verify that a category of interest has those, and my category is small enough, or I can find a nice functor by some other means to the category of sets, then I can extract a topological monoid which entirely determines that category, such that the principal actions or equivalently right congruences of that monoid determine the are equivalent to my original category C, which is useful for exactly the same reasons that classical Galwa theory is useful, because identifying the open congruences on monoid, while it's quite a mouthful, is a lot easier in general than studying the objects of my category C, or you can see from the field case how that can be true. So what next? Well, we haven't gotten all the way back to the start of the talk. So there is still the matter of identifying an algebraic situation. So for instance, you might not be convinced of the usefulness of the theory that I've sketched just yet, which is reasonable. It's a work in progress. But because I have these technical conditions, all I have to do is identify when a given algebraic situation, for example, taking a ring and some constrained class of algebras over that ring, produce a category of this form, and then I can just turn the handle and I get a semi-Galois monoid for that situation. That's everything for now. Thanks very much.